It's important we zoom into one rectangle or strip in this instant, but it doesn't really matter which one it is. We see that the rate of change of area is equal to the function. If we have 2 points A and B, then we see that the difference between those two equals the width of the strip. And we can see that we can get the height of the strip by getting the function of the midpoint between those two, giving an estimate of the area. We also see that decreasing the distance between A and B makes the strip closer to a rectangle and makes the area equation more accurate to the actual area underneath the graph. If we set A to B, then the difference between them will be infinitely small. Then it will be equal to the nearly infinitely small dx, which accounts for its infinitely small width, giving us an infinitely thin rectangle with the width dx and height f of x. So we can see how infinitely many infinitely thin rectangles can be used to fill the area under the graph between 2 points like A and B to get the most accurate possible area. I'll be showing how the sum of infinitely thin rectangles work with Riemann sums. We will be using the same logic as last time by imagining 4 rectangles with the same width all along a graph and a height equal to the function at the rightmost point. We can add these rectangles to get an estimate of the area, which is equal to f of x1 times f of x1 take away f of x0 plus f of x2 times x2 take away x1, and the process repeats with the x number increasing until all 4 rectangles are accounted for. We can say that this is equal to S4, which is also equal to the sum of f of xj multiplied by xj take away xj take away 1, which is continued for 4 units, as we can see in the sigma symbol, where j starts at 1 and goes to 4, so there will be 4 different expressions that need to be added together. We can also condense xj take away 1 into change in xj. This equals the width of the rectangles. We can insert this into the sum equation to get Sn equals the sum of f of xj times change in xj. N can be any number, but increasing it would decrease the width of the rectangle simultaneously. Only if there is a finite distance between x0 and xn that remains constant. We can use this logic to set n as close to infinity as possible to get Sn equals the integral from x0 to xn of f of x times dx. This is the equation that adds the infinitely many infinitely thin rectangles to get an area. In this particular example, the integral is definite, as there is a fixed distance between the 2 points of the area we want to find. Before we continue, I need to be clear about the 2 types of integrals. The first one is the definite one, which is just when there are 2 points like A and B in which we need to find the area under the graph between those. This is the only integral where we can find the area under the curve, and the fact that the 2 points A and B do not change and remain constant. The next one is the indefinite integral, where the points can change. range, like x is a variable, so the graph will go to whatever x is. This isn't particularly useful for finding areas, so we're not going to go any deeper into it. But it is used to find a range of functions, so I've added it just for clarity's sake. I will now show how to go from integration to differentiation to show how they're related. Firstly, we need to know that capital F of x is considered the antiderivative. And in the fundamental theorem of calculus, capital F prime of x is equal to f of x. This means we are able to use a reverse of the power rule when n does not equal -1. If f of x equals x to the power of n, then f capital of x equals x to the power of n plus 1 all over n plus 1 plus c. The c is a constant, and it is the constant that we remove when we differentiate a function. Secondly, I must point out that the integral from a to b of f of x times dx is equal to capital F of b take away capital F of a. To help you understand, I will use a real example where f of x equals x to the power of 3 and the integral goes from 2 to 4. Our objective is to find the area under the curve between 2 and 4 for the function x cubed. Firstly, we start with capital F of 4 take away capital F of 2, which then equals 4 to the power of 3 plus 1 and over 3 plus 1 plus c. Take away 2 to the third plus 1 all over 3 plus 1 plus c. We then simplify to get 4 to the power of 4 over 4 plus c, take away 2 to the power of 4 over 4, take away c. The c's cancel out, leaving 4 to the power of 3, take away 2 squared, which equals 64 take away 4, which equals 60, which is equal to the area. I also want to state why we should address it as net area. If we have the integrand from 0 to 2 pi of sin x times dx, then we see on the graph half of it is positive and the other half is negative. For this case, the areas cancel out, so in total it is 0. But in other cases, the total area could be negative, which wouldn't make sense because an area can't be negative, which is why it is better to address it as the net area gain or loss.